Alrighty, so on this worksheet, this is called Simple Oscillator Basics number 2. We have a 0.5 kilogram mass on a spring and it's pulled back a distance of 0.10 meters on a frictionless surface. When released, it oscillates with a frequency of 1.7 hertz. So first of all, I'm going to identify the things. So this is my mass. And it's getting pulled back a distance of 0.1 meters. So that's going to be from equilibrium to your minimum or to your maximum. And so that's your amplitude. So by definition, your amplitude then is 0.1. And when released, it's going to oscillate with a frequency of 1.7 hertz. That means that our frequency is 1.7. And it says, what is the period of oscillation? Well, I know that period is equal to 1 over my frequency, which means that that would be 1 over the 1.7 frequency that I have. So that means the period of my oscillation is 0.588 seconds. And so that'll be to go from your maximum all the way to your minimum and back again. So the amount of time that takes is your period. Using the period and other givens in the problem, what is the spring constant? Well, to do this, we're going to need to use the equation for the period of a spring, which is 2 pi times the square root of m over k. And we have everything except for k, which is the spring constant. So spring constant is k. So since we just found the period, our period was 0.588 seconds. So that's going to go here. So 0.588 seconds. And I'm actually going to make sure that I leave that number in my calculator so that way I can have a very precise number later. And that'll be equal to 2 pi times the square root of our mass, which was 0.5, that was given in the problem, over k. All right, so to solve for the k, what I'm going to do is I'm going to start by dividing by 2 pi on both sides. Now, this is a really common mistake. It sounds pretty simple, but when you do the 0.588 blah, blah, blah divided by 2 pi, make sure that you're putting parentheses here. If you don't put parentheses here, you're going to be dividing by 2 and multiplying times pi instead of dividing by 2 pi, which is going to give you 0.936. And then to get rid of the square root, you're going to square both sides. So that cancels out this. And then you have k on the bottom. So you can either cross multiply or do this, where I multiply both sides by k, and then the k's on the right side will cancel out. And then because it's k times this number, I divide by the 0.008765 on both sides to get a k of 57.046. And the next question says, what is the amplitude of the oscillation? Well, the amplitude is just how far this goes from equilibrium. And that was actually given right here in the problem. It told you that it was 0.10 meters. So that's all we need to do. In part D, it's asking for what the maximum velocity is. So to find that, you're actually going to use the conservation of energy. And so in conservation of energy, we're going to think about our maximum displacement. Our maximum displacement, it's not moving, so our velocity will be 0, which means that all of the energy will be spring potential energy and kinetic will be 0. And then at equilibrium, this is where it's in the middle. Where all the forces are balanced. There's no spring pulling it to the right. There's no spring pulling it to the left. Well, that's because the distance the spring is compressed is 0. And so that means that when you do 1/2 kx squared, you get 0. So that's why my spring potential energy is 0 here. And then kinetic energy is going to be 1/2 mv squared. And that's all the energy because that's what is left. All right, so once you have that, we're going to go ahead and plug it in. All right, so the only thing we have on the left side is spring potential energy, so that's 1/2 kx squared. On the right side, the only thing we have is kinetic energy, which is 1/2 mv squared. So what I'm going to do is just set those two things equally to each other. So the spring potential energy being when it's all spring, and the kinetic energy being at equilibrium where all the energy is in kinetic energy. I don't like having the 1/2, so I'm going to multiply both sides times 2. That'll cancel out the 2 and the 1/2, and I'll be left with k times x squared is equal to my mass times velocity squared. All right, and then k we have from before, that's 57.046. Our x is our amplitude, that's 0.1. Don't forget to square it. That's because that's the maximum distance that it was stretched, so that's the x that we use. And then mass was 0.5, and our velocity is what we're trying to figure out. So then I go ahead and put this in my calculator, and I get 0.57046. I'm going to divide both sides by 0.5 to get v squared by itself. And then the opposite of squared is square root. And so I get a velocity of 1.068 meters per second. All right, so that's cool. So now I have my maximum velocity. And so now I just need to find my maximum acceleration. So there's two things I need to remember. One is Hooke's law. Hooke's law is that the force from a spring is equal to K, or your spring constant, times the distance you've stretched it. So again, thinking about where our maximums are, wherever you have stretched it the farthest, that's where you're going to have the biggest force. Well, that's going to be when x is at its amplitude. That's where our force will be at its maximum. And when that force is at our maximum, that means that our acceleration will also be at its maximum. So we know that because if we were to do a net force equation, the sum of the forces in the x direction, the only thing acting on this to make it speed up or slow down is the force of the spring. And that's going to be equal to mass times acceleration. So this part here, the kx, I'm going to put in for the force of the spring. So that's kx is equal to my mass times the acceleration. So our k was 57.046. Our x was 0.1. Our mass is 0.5. And so we get an acceleration of 11.409 meters per second squared. All right, so then we just need to graph it.
All right, so in part F, we need to now go ahead and make position versus time graphs, velocity versus time graph, and an acceleration versus time graph to represent the motion of the spring. For the position versus time graph, the first thing that we need to think about is how much time it takes for one full oscillation. And that's going to be the period. So the period that we identified in part A was that the period is 0.588 seconds. So that means that for one oscillation, it's going to take 0.588 seconds. And originally the spring was pulled to a positive position. So we're going to start at that maximum position. And then at 0.588 seconds, we need to be back at that same position again. So I'm going to label this as 0.588 seconds. And this is important because all of these all of the different dotted lines that I have on here are so that way we can keep track of these times across all of the different position versus time, velocity versus time, and acceleration versus time graphs. So hopefully it'll just help us to line things up. Now, halfway through this time is going to be when it is at its minimum. So if we're at our maximum at 0.588 seconds, then that means that we're going to be at a minimum position halfway between that. So that means that right here, this is 0.294 seconds. All right. And then when you pull this back, you should think about how, okay, it's not moving at that point in time. And then just remember that the slope on a position versus time graph is the velocity, and the slope on a velocity versus time graph is your acceleration. So thinking about my position versus time graph, we have it starting at a big position and it's not moving. So that means that my velocity is 0, so it's going to start flat. And as it goes, it's going to speed up. And it's specifically going to speed up going backwards towards 0. And so we start flat and we're going to have it curve down, just like a cosine curve. Once it passes equilibrium, and equilibrium is like our 0 line here, it's going to start getting less and less and less steep until you get to your maximum. And so I'm going to just make sure that I'm hitting those spots, that it's evening out at the middle and then curving back. It doesn't have to be beautiful. And then again, at another half again, it's going to be back. There we go. Okay. So now we have our position versus time graph. And we need to make sure that we have our maximum position labeled. So this maximum position is going to be our amplitude. And so we have to remember what the amplitude was, because that's going to be our maximum position. And on here, our amplitude was 0.1. So that means that that height right there is 0.1. And that also means that our minimum is going to be negative 0.1. And then one thing to make sure is that when we're drawing these graphs, we make sure that we're having the times happen at the same time up and down. So this 0.588 seconds, it's going to take 0.588 seconds for one period. It doesn't matter if I'm talking about position versus time or acceleration versus time. So you need to make sure that you put your time stamps in on the other axes as well. And that's why I have these vertical lines, is it just kind of helps to keep things lined up. All right, now we were already talking a little bit about how this starts with a velocity of 0. That's when it's pulled all the way back. So that's when it's not moving. That means that my velocity here is going to be 0. So that means that I need to make sure that my velocity at time 0 is 0. And that would also mean that one period later, my velocity is going to be 0 again. So I'm going ahead and just adding those dots. Next, I need to think about if my velocity is going to go positive or negative. Again, remember that the slope of a position versus time graph is acceleration. So here we have a negative velocity, and that's the steepest part of our negative. So that's where we're going to have our biggest negative velocity. And then here our slope is 0. That's why our velocity will be 0. And here we have a positive velocity, so we're going to have our maximum positive velocity there. And that's also where our spring potential energy is 0. So just remember, like at this point, this is where spring potential energy is 0. And that's why our maximum kinetic energy is going to be at that point. So when we have our maximum kinetic energy, that's going to be when our spring potential energy is 0. All right, so we're going to go ahead and draw the curve here. And then the next thing we need to do is put in those maximum and minimum velocities. So up here, we did find that maximum velocity in part D. We found that it was 1.068 meters per second. So we just need to label this 1.068 meters per second. And that would make our minimum negative 1.068. Last but not least, we have acceleration. Okay, so acceleration is the slope of your velocity versus time graph. So here we're starting with a negative slope, which means we're going to start with our biggest negative acceleration because that's where our velocity is 0. That means that that's going to be where it's moving the fastest, or it's moving the slowest, which is going to be when it's at its maximum position. And when it's stretched to its maximum position, that's where the force is going to be the biggest, because force is equal to kx. And when you have a bigger force, you have a bigger acceleration. So that's where my acceleration is going to be its biggest negative. And then here I have a slope of 0. So that's where my acceleration is 0. Positive slope here, positive acceleration. 0 slope, 0 acceleration. And we'll just keep repeating that pattern. And last but not least, we just have to put in those maximums and minimums for the acceleration. So if I come up here in part E, we found the maximum acceleration was 11.409. So that'll be our biggest here, 11.409. And that means our minimum will be negative 11.409. Okay, so a couple things just to make sure you remember. Don't forget about labeling the period on all three graphs. And don't forget to give me those maximums and minimums. And as a side note, if you are in calculus by chance, you will notice that the first curve from position versus time graph will give you a cosine curve. And the velocity is a negative sign. And acceleration is a negative cosine. And so remembering that the derivative of a position versus time graph is your velocity, the derivative of velocity is acceleration. You'll notice this derivative of cosine is negative sine. The derivative of negative sine is negative cosine. So we can do it algebraically just looking at the slopes, or you can do it with calculus. But it's kind of fun to see it both ways. Let me know if you've got questions. Otherwise, good luck.